All right, guys, let's go ahead and start working on simple machines and get our notes finished for today. Now, what are the 6 types of simple machines? You have the simple lever, the pulley, the wheel and axle, the wedge, the simple inclined plane, and the screw. And we're going to talk about each one of these in more detail. Now, simple machines are divided into 2 families. You have the lever family and you have the inclined plane family. Now, there are 2 principal parts of all levers. So we're talking about the lever family first. All levers have a rigid arm that turns around a point called the fulcrum. And the lever family consists of the simple lever, the pulley, and the wheel and axle. Now, levers are divided into 3 classes, and I've actually shown you a picture of each one of these classes. First class levers, second class levers, and third class levers. Now, this is the picture you should be seeing in your notes. And if you'll look, first class levers always have the fulcrum in the middle of the output force and input force. Okay, and the simple lever is a lot like the seesaw that you see on a playground, right? It's just the second class and third class are a little different. But if you look, the first class always has the turning point in the middle, and the output force is on one side, the input force is on the other. An example is a pair of pliers. Now remember, input force is what I put into the machine, and remember the handles are where we squeeze the pliers at, so that's where we put the input force. The fulcrum, as you can see, the turning point, which it's got it labeled right there, the turning point is in the middle, and the output force is where the machine does the work. So the end of the pliers is where the output force is. So the fulcrum is in between the output force and input force. With a second class lever, you're going to have the fulcrum is going to be at the very end, the output force is going to be in the middle, and the input force is going to be opposite the fulcrum. Now this would be like a wheelbarrow. As you can see, the fulcrum of the wheelbarrow is labeled at the very end, okay? Now, input force is where we do the work. So as you can see, it's on the handles of the wheelbarrow because that's what we have to pick up. The output force is where the work is done, and so that's where the load is carried in the wheelbarrow because that's the that's the work that's being done by the machine. Now, third class lever, you still have the fulcrum on the end, and input force is in the middle, and output force is opposite the fulcrum. Now, I do not really like the picture that they have for you on this worksheet. What I like to think of is a broom. A broom, you have the fulcrum is your hand, or is actually using your hand to make the fulcrum, where you put your hand at the top of the broom. You put your other hand in the middle of the broom to cause the force, so the input force is in the middle of the broom. Then the output force is at the end of the broom where the bristles are because that's where the work's being done. Now, let's go ahead and continue our notes. Now, that was the simple lever. Now, the pulley is also in the lever family, and it's a modified lever. Instead of having a rigid arm, like looking like the seesaw, it actually has a rope, usually, that goes across the fulcrum. And so the point in the middle of the pulley is like the fulcrum of a lever. The rest of the pulley behaves like the rigid arm of a first-class lever. And if you'll notice, you have some pictures at the bottom. You need to know that a single fixed pulley has a mechanical advantage of 1. You also need to know that a single movable pulley has a mechanical advantage of 2 because it actually helps you out a little bit more because the pulley is movable. Then as you add numbers of pulleys, your mechanical advantage is going to increase. So when we add 2 pulleys that you can see to the far right of your picture, that means the mechanical advantage is going to be 3. So make sure you understand pulleys in relation to their mechanical advantage. Now let's look at the last member of the lever family. That's wheel and axle. A wheel and axle is a lever or pulley connected to a shaft. An example would be a steering wheel. a screwdriver, and then cranks. These are all wheel and axle machines. And it's basically where you have one part that is remaining still and the other turning. And so it's just like the simple lever that we talked about, but it's just a little modified. Now let's talk about the inclined plane family. The inclined plane family consists of the simple inclined plane, the wedge, and the screw. Now, how does using an inclined plane change the force required to do work? So basically, how does that actually help us? It helps us because pushing an object up an inclined plane requires me to put in less force than if I had to lift that object the same distance. I'm sorry, these are out of order. But now the wedge. The wedge is a modified inclined plane. A wedge turns a single downward force into two forces directed out to the sides. Now, an example of this would be an axe. You know how an axe has two ramps that come together to make one point? That's what a wedge is. It's two simple inclined planes put together to make a sharp point so that you can use it as a machine like an axe. A nail is an example of the same thing. It's two small little bitty inclined planes put together to make a really sharp point. And they're used as fasteners. Nails are used as fasteners. Now, the last inclined plane family member that we're going to talk about is the screw. Now, if you will look really closely at a screw, if you have one at your house, look at it. And if you look really closely at it, it looks like it has a tiny inclined plane all the way up the shaft of the screw. And it looks like you could, if you had a little bitty person that could walk all the way up, it looks like a ramp all the way up the screw. And that's what makes the screw a part of the inclined plane family, because it uses that ramp, continuous ramp, to help it become a machine. Now, compound machines. A compound machine is a machine made of more than one simple machine. So it's when you take more than one simple machine and put it together to make a compound machine. So what simple machines make up a pair of scissors? I would like you to pause the video and think about this just for a second. A pair of scissors uses two first-class levers joined at a common fulcrum. And if you'll remember, scissors, or even look at your house, on the handles is where you put the force, so that's input force. The fulcrum's in the middle, which is the bolt that's in the middle of the two first-class levers. And then the work's being done at the end, the output force into the scissors. They also, each lever has a wedge, and so that helps cut the paper. So it's two first-class levers and also two wedges that make up the compound machine of scissors. Now, let's talk about efficiency of machines. We've discussed all of the simple machines now, but we need to know sometimes how efficient those machines are. So, how much of the work done by a machine is actually useful work? Now, I'm going to go ahead and tell you something. A machine is not perfect, just like humans are not perfect. So a machine cannot be 100% efficient. That would be the perfect scenario, but it just never happens. Now, this is what I was talking about. Only a portion of the work done by a machine is useful work. And that is work that the machine is designed or intended to do. Not all the work done by a machine is useful work. And a lot of times the reason why it can't be 100% efficient is because of friction. And so that lessens how much work can actually be done by the machine and how efficient it can be. Now, you need to remember this. Work output is always less than work input. That means whatever input that we place into the machine, you're going to get less work out of it. Okay? You can never have work output be more than work input. So always know, because we're fixing to learn how to calculate efficiency of machines, and they're going to give you two numbers, and you're not going to know which one's which. But if you just always remember, work output is always less than work input. Now, efficiency is the ratio of useful work output to work input. And the definition of efficiency is a quantity or number, usually expressed as a percentage, that measures the ratio of useful work output to work input. Now, efficiency equals useful work output divided by work input. All right, this is what I told you I was going to show you. Efficiency equals work output, WO, divided by work input, WI, and then you multiply that by 100 to get the percentage, okay? Now, our circle is not going to include the 100. You just have to know once you calculate it that you need to get the 100, all right? And what that does is if it gives you 0.25 when you calculate it, multiplying it by 100 allows you to change it to the percent. So it's just moving the decimal place. And if you're ever given efficiency and you have to calculate work output or work input, you have to get it back to decimal form before you calculate. Never leave it in percentage form when you're calculating. All right, remember, this is a confusing problem because we have, if a pulley is able to do 50 joules of work, but you need to lift a piano that requires 80 joules of work, how efficient is the machine? Now, normally we would say that work input is what I put into the machine. But this I can't tell what it is. And so our other rule, if you'll remember, work output is always less than work input. So that means that work output, if it's always less than work input, that means it's 50 joules. Work input is 80 joules. And then it asks us to find the efficiency. So efficiency equals work output divided by work input. Let's go ahead and fill that in with our numbers. Work output is 50 joules and work input is 80 joules. And when you calculate that, you're going to put in 50 divided by 80. And that's going to give you efficiency of 0.625. Now remember, we like to portray efficiency with percentage, so we're going to multiply it by 100 or move the decimal 2 places, whichever you would like to do. And when we multiply that by 100, that gives us 62.5%, and that's the efficiency of this machine. Now, I would like you to go ahead and do practice problems 1 and 2, come back to stop the video, and then resume the video when you're ready to check your answers. Now, remember, work output is always less than work input. All right, that was one practice problem. Now I want you to do practice problems 1 and 2 by yourself and pause the video. When you're ready to check your answers, resume the video. All right, the answer to this is 75%. If you did not get this answer right, stay with me. I'm going to show you how we got it. If you did get it, go ahead and fast forward. It says Alice and Jim calculate they must do 1,800 joules of work to push a piano up a ramp. However, because they must also overcome friction, they actually must do 2,400 joules of work. What is the efficiency of the ramp? So it's asking us what the efficiency is, and we need to know if what work output is and what work input is. Remember, our rule is output is always less than input. So our work output has to be the 1,800 joules. The work input is 2,400 joules. So efficiency equals work output divided by work input times 100. Let's go ahead and plug in our numbers. 1,800 joules divided by, 2,400 joules. And that equals 0.75. And when we multiply it by 100, we get 75%. Now, let's go ahead and go to the next problem. Now, our next problem, it says it takes 1,200 joules of work to lift a car high enough to change a tire. How much work must be done by the person operating the jack if the jack is 25% efficient? Now remember, efficiency equals work output divided by work input. And we'll do our circle. Let's see. We have work output over work input. And the other one is going to be efficiency. Okay? Now, it tells us that our efficiency equals 25%. Now, it takes 1,200 joules of work. And you don't have the other number to know which one's less. Let me show you where your hint is. It says, how much work must be done by the person operating the jack? Okay, we know that the work done by the person is going to be work input. So that means that's the question mark, which shows us that work output is the 1,200 joules. All right? So now, work output is what we're looking for, and if you cover it up on the circle, it's going to show you that work input equals work output divided by efficiency. Now, what rule did I tell you before you plug in efficiency into a formula? You can't have it in percentage. You've got to put it back to its decimal place. And if it's at 25%, we multiplied it to 100 to get it to this part. So we need to divide it by 100 to get it to 0.25. So work input equals work output of 1,200 joules divided by 0.25. So you say 1,200 divided by 0.25, and that's going to equal 4,800 joules. And that's how much work has to be done by the person operating the jack. Now, we need to do a summary. So this is what I'd like you to do. I would like you to do a tweet summary, and that means in 140 characters or less, you explain what this video is about and you summarize the most important parts. Make sure you have that ready for class, and we'll see you in class.